Welcome to IAPE. My name is Emmanuel Rivera and I am the project manager of Team LiDron. Team LiDron's members are Rafael Alvarez as our obstacle avoidance group leader with his members Gabriela Delgado and Jorge Torres, Daniel E. Torres as our architecture group leader with his members Omar A. Rodriguez and Samuel A. Vidot, and Denis Martir and Veronica Rivera in our hardware group. We're still working on our same implementations using three LiDAR sensors: the M16, the Velodyne Puck Lite, and the letter 1. We'll receive a waypoint coordinate and the drone will lift up and go to this coordinate. If it encounters an obstacle, it will go around it or over it, scanning using the LiDAR sensors. When it arrives at this waypoint, it will circle around a 6-foot radius of this waypoint and it will locate possible landing zones. When it sees a possible landing zone, it will go to this point and it will descend while rotating to see any obstacle that can sabotage our landing.
This semester, the obstacle avoidance and flight planning team, led by Rafael Alvarez and composed of Gabriela Delgado and Jorge Torres, had an objective: to create an image processing algorithm capable of detecting obstacles that may pose a threat to the safety of the UAV. Using Visual Studio Code integrated development environment to write in C++ language, the team used different filters and functions from the OpenCV library to process the video provided by the Intel RealSense D435 camera. The filters used reduce the size of the three-dimensional RGB matrix to a two-dimensional matrix, containing only values of the color gray. After reducing the matrix, other filters were applied in order to identify and draw the edges of the objects that were captured by the camera. This image processing algorithm was originally completed using Windows OS, but at the end of the semester, the team was able to download OpenCV library in a VirtualBox running Linux and use CMake to build an environment and compile the code in the terminal. This image processing algorithm helped us identify objects to move to free areas. Obviously, this process is repeated for real-time in-flight obstacle avoidance, and after the system processes the image gathered with the depth camera using the image processing algorithm, it will start the avoidance stage. Through the use of ROS, the system will be able to move freely to an area free of obstacles.
The team is also working on reading LiDAR data from the Velodyne Puck 16 sensor using ROS and LiDAR SDK on the single board computer. In this flowchart, we can see how the data is initially processed and how Point Cloud Library converts the raw data into a message which will be used for the safe landing zone algorithm.
We are also working on reading LiDAR data from the Velodyne Puck 16 sensor using ROS and the LiDAR SDK. We ran into problems with the ROS LiDAR library, so we decided to implement the ROS node ourselves using LiDAR SDK Python bindings. These scripts are yet to be tested with the actual sensors and onboard computer.
The architecture team worked on identifying the necessary data transformations to pre-process the data from the generated point cloud map. After converting the frame coordinates from the point cloud map, various steps are taken for the safe landing zone algorithm. These steps are filtering, which can improve the processing by removing points that deviate too much from their average, downsampling, which reduces the captured points while it keeps the structure of the point cloud intact, and a voxel grid filter is used to perform discounts downsampling. Registration and matching. This technique finds common features in different datasets and stitches them together, which is useful to reduce the uncertainty of a post-estimation on where the drone lies within the point cloud map. Segmentation is the process of partitioning that dataset into different blocks that specify specific criteria. This can fit different models. In this problem, the team wants to fit a plane surface, and from these steps, various planes will be compared to identify the detected spot.
This is the 3D model of the placements we have for the components of the drone. In the bottom part we have the Velodyne and M16 holder. There is a hole in the bottom so that the M16 can point downwards. We're also planning on placing the smaller battery beneath the frame as well. There is still the task of building a mount for the RealSense camera, but it will be placed on the front like so. In the first floor we'll have the cable management. In the second floor we have the pick sock and the odroid, and on the third floor we have the LiDron sensor and the bigger battery placed right on the center of the drone.
For any questions, you can contact us using the QR code. Thank you for all your attention.